Good afternoon to all of you. And today we would like to learn about the classical theory that explains us that why there happen to have some of the materials which are good conductors of electricity. And this model was given by Drude. So it's Drude model of metals, let's say, like that. Yes. So, there are some of the important assumptions of this model, and this is basically a model that describes the conducting properties of metals, or you call them as conductors. So let us talk about the basic assumptions first, because when you will look into a material, this material is basically made of atoms, and these atoms they're bonded with each other, and they make up the particular kind of material. And talking about the atom, we know it has a positively charged nucleus at its center, and it has revolving electrons. And these electrons are bound to the respective atoms that you have in your material. Right? So you have a situation in which there are atoms. Atoms have electrons, but these electrons are bound in their shells. And these atoms make up your materials. And our target is a material to which, when we apply the potential difference, it conducts. So, applying potential difference means you are doing an external work to move the charge of the conductor from one point to another point. So, what we have is, we will be talking about the Drude model. This model is purely classical in nature. And there are some of the important assumptions we have to keep in our mind, and then we have to predict some of the important properties of these metals. So, talking about this model, the first thing is that in metals what we have free electrons. We have free electrons. That means at room temperature there are electrons which are free inside the metal. But I should say you that majority of the electrons are bound, because it's only the electrons which are present in the outermost shell. They are available in what's called as conduction band. But they are free, but they cannot leave the metal surface. They are free inside the metal, but they cannot leave the metal surface. Why they cannot leave the metal surface? Because of the presence of kernels. And kernels means the positively charged ions that are present inside. Right? So this is the very first assumption, the very first argument, that electrons are free inside the metal. But they are not free to leave the metal. They cannot leave the metal. The next important point is, now when we say electrons, they have a charge. They have negative charge, right? And each electron has a charge 1.602 times 10 to the power of minus 19 coulombs. So as a convention, it is minus. But its magnitude is this much. So it has a charge, and we know that like charges repel and unlike charges attract. So that means if you have a bunch of electrons, in reality, between these electrons, there should exist electrostatic force. There should exist electrostatic repulsion, because they are like charges. But within the framework of this model, we assume that between the electrons, there is no force. The presence of one electron does not disturb another electron. So every electron that's taking part in this material is independent of every other free electron. Got my point? Right? So this is another important argument about the drug model. Getting my point? The next important thing is, okay, we have taken into account the electrostatic force, which we assume is absent between the electrons. Now, within the classical framework, we know that electrons are particles. An electron has a mass. And mass of electron is how much? It is 9.1 times 10 to the power of minus 31 kilograms. Right? Come in. Okay. So they have the mass, okay? And if they have the mass, these are the point masses. Is there any influence of the gravity on these masses? What we do here is we assume that gravity does not have any influence on these masses. So there is no gravitational force acting on these electrons. Right? Now, you have a large number of electrons inside the metal, and these electrons, certainly they'll be colliding with each other. And when the electrons will collide, what do you expect from that? What do you expect from the collision of electrons?
If we can't take assumption, then they will repel each other. But if we have taken assumption, then
so there is a possibility of transfer of energy, and there is a possibility of no transfer of energy. Now, if energy is transferred in a collision between two particles, this collision is called inelastic collision. And in inelastic collision, the momentum is conserved, but there is no conservation of energy. In fact, during the collision, the one particle will not only transfer its energy to the particle with it which is hitting, it may lose the energy to the system in which this collision is taking place. So we have another kind of collision. It's purely idealistic in nature. And this collision is called elastic collision. And in case of elastic collision, there is conservation of both energy and momentum. You don't have any energy transfer. You have the momentum transfer, momentum is conserved. The momentum before the collision is equal to the momentum after the collision. So, in the drug model, we assume that these electrons have elastic collisions. So, they don't lose any energy. They don't do that. There is conservation of energy, and there is conservation of momentum. There are other things that are defined in this framework. The next thing is relaxation time. Now see, one electron will collide with another electron. Okay? The time that it will take to collide and leave, this time is called as relaxation time. Relaxation time. And this relaxation time is symbolized as tau. Right? And there is another important term that we have that's called free path. Okay? The path that one electron has before it collides with another electron is the free path. Now, if you take the average of all the paths that an electron will have, assuming the rest of electrons are at rest, the average of all the paths that this electron will encounter is called as mean free path. It's called as mean free path. So these are some of the important postulates of the drug model. And in fact, what we have in real materials is the opposition. When you apply the potential difference across a conductor, you have the flow of charge. And the rate of flow of charge defines current. And this flow is opposed. There is an opposition offered to the flow of this charge. And this opposition, the overall opposition to the flow of the current, is called as resistance. Right? Now, keeping in all these points in our mind, we would like to take an ideal situation. I would like to assume a conductor, say like this. This conductor has free electrons. Now you know what's the meaning of free electrons. This conductor has a geometry. It has a length L, and it has area of cross section, and assuming this area of cross section to be A. And when you apply the potential difference, what do you expect? You expect the flow of charge, because electrons are free. So once electrons are free, you are providing a slope to the electrons. And that slope you are providing by the battery. And this battery is providing a potential difference equal to V volts. Right? And what I assume, so once you have this kind of situation, you will have flow, you will have the current. This is the convention. the direction of current is always opposite to the flow of
Electrons.
electrons. So that means if I assume that the current is flowing in this direction, that means the electrons are moving opposite to this conventional direction. Right? Now what I have a conductor, its length is L, it has an area of cross section, but it has electrons in it. Okay? Now if I assume that N is the number of electrons per unit volume. You may also call it as number density. Right? I know the definition of current. And what's the definition of current? If its symbol is I, it's defined as the rate of flow of charge. Now I want to calculate this charge. This Q is the charge that's taking part in the current. Right? And this charge is Q. And how can I write down this charge? This Q will be, it will be charge of the electron, because the only contribution in your conductor is because of electrons. It will be times the number density, right? N is the number of electrons per unit volume in your conductor that you have assumed. It will be times the volume of the conductor. And volume of the conductor is what? It is L into A. Now you see, LA will give you the volume. If you multiply with it number density, the volume and volume will cancel. You'll get the actual charge that's taking part. So this is my charge that I can account is taking part in your conductor. So I can use this equation in the definition of the current. So I will be E-N-A-L by T. Right? This is it. Now, this is L is the length of the conductor and T is the time. Now here we will introduce another important definition of the metals, of the electrons inside the metals who are taking part in electric current. And what's that? That's drift velocity. Now what do you mean by drift velocity? That's my question. Yeah. Now see, when you are not applying any potential difference to the conductor, there are free electrons, right? And these electrons have motions. They have random motions. Are you getting your point? They have random motions. So that means there is flow of electrons. No doubt that flow is in different directions, right? So when electrons are in motion, you cannot say that there is no current. There is current because the electrons are in motion. But these electrons have velocities. And velocity is a vector quantity. And the motion of these electrons is random. That means velocities are random. So on an average, if you calculate the average velocity of the electron in that randomness, that will be equal to 0. Because all the velocity vectors that will take part in your conductor will cancel out. Right? But now I am applying the potential difference. Right? When I am applying the potential difference, what is happening? It's a wrong word basically to say particular direction. This is just for the sake of understanding that I have put those arrows. It's not like that. Electrons don't have that preferred direction. Then current should have been a vector quantity. Current is not a vector quantity, current is a scalar quantity. So what is happening here? What's happening? You have some of the electrons which are able to move in that particular direction. But in the meantime, there are collisions. They are coming out, they're moving on with these collisions. Are you getting my point? Now, the velocity of those electrons who are making it to the other end, who are moving to the other end, that velocity is called drift velocity. And you know how to calculate it. You have done it. And can you tell me how much is this drift velocity equal to? It is, yeah? No, that I am defining here. But what is drift velocity equal to? Oh, don't give me the numbers. Give me an expression. The magnitude of this drift velocity. Yeah, it is E tau by n. Right? Where E is the charge, E is the electric field, because you are applying the potential difference, you are applying the electric field, right? And tau is the relaxation time. And m is the kind of charge that's taking part in your conductor. And that is electrons. So m refers here to the mass of the electrons. So this L by T is also what? This is the drift velocity. So I will be equal to En A Vd. Right? Well, this Vd is what? This Vd is drift velocity. But Vd, we already know, is equal to E tau by n. So I can use this drift velocity in this equation. Because I'm writing the current that's flowing in your conductor. So what will be that? So I will be equal to ENA. Now instead of Vd, I'll be writing the magnitude of this drift velocity E tau by n. This should be clear, right? Now I can make some of the manipulations. So I will be E square n A tau by n times E. Right? Now talking about this E, what is E? E is electric field. And there is a relation between electric field and the potential difference. What's that? If you have to write down that, so E is V by, let me use L here because I have started with L. So if you want to define the electric field for the conductor that I wrote down, it has a length, it has electric field. So this electric field is the potential difference divided by length of that conductor. So for this electric field, I'll be using V by L. So what I'll get? I'll get I is equal to E square NA tau by NL times V. Right? So what will be V? V will be NL by E square N A tau times I. Right? So V is the potential difference you are applying to this conductor, which has taken all of these assumptions under consideration. And I is the current that's passing through that conductor. And everything in the bracket is a constant. You don't find anything here which is a variable. So everything in the bracketed term is a constant. The length is constant. The mass is constant. And we have already an experimental result. That's called Ohm's law. And what's that? That is V is equal to IR. So we have given a theoretical explanation to the Ohm's law. V is equal to IR. Where this R is what? R is the bracketed term. So you have Ohm's law and you have R. R is the opposition. The opposition offered to the flow of current when you are applying a potential difference across a conductor. So what is that equal to? That is mL by E square N A tau. Isn't it? And all of you know that this resistance is measured in ohms. Right? Now, one thing is clear. But you know that there was always a flaw in my assumptions. That was not reflecting the reality of your problem. Are you getting my point? Are you getting my point? But these assumptions work. And you can see that they work because you have achieved Ohm's law from these assumptions. So, can I write something like this? R is equal to M by E square N tau times L by E. Now this bracketed term is called what? It's called resistivity. It's called resistivity. So you have another relation. What is that? R is equal to rho L by A. Now you have a definition for the resistance. And you can see that this resistance has a dependence on the geometry of the conductor. So for a conductor whose area of cross section is large, the resistance will be low. And for a very long conductor, the resistance will be large. Are you getting my point? So this is how we achieve resistance. And we also know this rho. What is rho? This is resistivity. How much it was? It was M by E square N tau. M by E square N tau. And you can define this resistivity from this equation. So resistivity is nothing but resistance, provided you have a geometry. So if I choose a wire of length 1 meter, area of cross section 1 meter square, think of that, how huge that will be. That will simply give us the resistivity. So the resistance of that material will be equal to its resistivity. And you can also see that this resistivity has inverse relation with relaxation time. Now you can see, if this relaxation time increases, what will happen to the resistivity? It will decrease. If this relaxation time decreases, what will happen to rho? It will increase. Are you getting my point? Now, what is that important resource that we have present in nature that can increase or decrease this relaxation time? This is my question to you.
Temperature?
Yes, it's temperature. So if you increase the temperature, the relaxation time will decrease. There will be, the collisions between the electrons will be fast. So Increasing temperature means decreasing relaxation time. Decreasing relaxation time means increasing resistivity. That means increasing resistance. Are you getting my point? So the resistance of these materials should increase if you increase the temperature of that system. And this equation is valid at room temperature. And similarly, if you go in reverse direction, you move below to 0 degrees Celsius. In the negative side, what do you expect? You expect that relaxation time will increase. Okay? They will take more time to collide. So if they will take more time to collide, the relaxation time will increase. So if relaxation time increases, the resistivity will decrease. And this was the experiment that was performed by Kamerlingh Onnes in 1930. He was just measuring the resistivities of metals at very, very low temperatures. Could you tell me what happened? What happened? One fine morning, maybe it was 1911, he was taking mercury to very, very low temperatures, and he was using liquid helium. So that he was taking the temperature surrounding mercury to a temperature which is equal to 4.2 Kelvin. Could you tell me what he observed?
Increase in conductance.
He didn't see increase in conductance. He observed there is no resistance. He observed there is no resistance in mercury. He had discovered a material which is called as superconductor. And you can see that how a simple argument can lead us to a discovery. Discovering a material which has no resistance. No resistance means no loss of energy. No loss of energy means it will go on forever. Are you getting my point? So at least you can have an idea. At least you can have an idea that if this relaxation time goes large, the resistivity will go down. Okay? And then you cannot explain superconductivity by the drug model because it's a classical model. But I was trying to put something in, some curiosity in your mind, that a simple idea can take you to a discovery that will change the course of the world. Do you have any questions? You don't have any questions? So shall we stop here? Okay. Okay, I'm very thankful of you that you have remained in the class. I hope you have learned something from this deliberation. So with this, I would like to say you goodbye.